All right. Hello, everyone. Welcome back to Historical Geology 1404, and may the 4th be with you today, right? Yes? Yes, this will be my pointer today. I won't leave it on, though, because the noise would be very distracting and will probably mess up the microphone. All right, so today is your last lecture day. Boo. Boo. Okay. You're getting the last little bit of new content today, and we are having our final exam review today. After class today, I will open the final exam and the lab exam, and you will be able to take those at your leisure until Thursday at midnight. Okay? Thursday at midnight, course closes. I come in first thing Friday morning. I grade everything. Okay? At that point, nothing else can be turned in. So it'll be final. Please make sure you have all your notes submitted. If you want that extra credit, make sure you have all your labs submitted. Prioritize the things that cost or that are worth actual credit before you prioritize the extra credit things. Your notes are important, but they are meant to help you with your exams. If your choice is upload 14 files of notes or, study or turn in my final or my lab exam or do an extra good work on a final or on another lab, always choose the points because they will count against you if you don't do well enough in those. Whereas extra credit, if you don't do that, there's nothing counting against you. It's only upside if you turn it in. Okay? There is downside if you don't turn in the actual work. So please prioritize that. What else? Oh, Wednesday, in 2 days, we are going to have our, bless you, we are going to have our movie night, movie day. Not having it at night. We're going to have it here during class during the day because we are still required to have class session that day. All right? Used to be I could just say, all right, we'll take the last day of class off. We have nothing to talk about. Have fun. Enjoy your extra study time. I'm not allowed to do that anymore when I have high school students. Dual credit students are still required to be in the classroom. So we will be here. We will have Jurassic Park playing. That was the winner. There will be a short extra credit thing that you can turn in about the movie, talking about the science that they used in the movie, how it works, how it doesn't work. You can also use that time to help finish up whatever other assignments in my class or other classes you have left at that point in time. Okay? Any questions about how the rest of the course is going to play out? Yeah? No? All right then. Any questions about what we covered last week? We left off with the Mesozoic. Give me a few highlights from the Mesozoic. Huh? Dinosaurs, right? Isn't that the biggest highlight from the Mesozoic? Dinosaurs are awesome. We love dinosaurs. Who doesn't love dinosaurs? Don't raise your hand. You don't want to show your face. No, we all love dinosaurs. So the Mesozoic, that was a fun time. What happened at the end of the Mesozoic? Use your words. The asteroid, yes. An asteroid hit, aka a celestial object made out of rock and metal. That was the extinction at the end of the Cretaceous. Okay? Now we're picking up, I should say, with the Paleogene, which starts 66 million years ago and goes to 23 million years ago. You'll often see the extinction at the end of the Cretaceous called the KT boundary, or the KT extinction. Why do we call it that? It's kind of shorthand. It looks like this, K/T. K is the symbol that we have on geologic maps for the Cretaceous. Even though the Cretaceous starts with a C, we use the K because the C was already taken by the Carboniferous. Okay? There are actually several ages that start with the C, the Cambrian, the Carboniferous, and the Cretaceous. Carboniferous was identified first and therefore claimed the C first. Cretaceous we designate with a K because it makes the same sound but isn't the same letter. And the Cambrian, you may have noticed looking at your assignments, you may have noticed that the Cambrian, it's not actually on here, looks like a C with a line through it like that. Okay, so that's just our designation for the Cambrian. 3 different ages that start with the same letter. We just tell them apart as best we can like that. All right, so the KT boundary, the Cretaceous extinction. All right, so what did we lose? Dinosaurs, kaput, no more. With one exception, avian dinosaurs survived. Remember that? Birds are the descendants of those avian dinosaurs. So technically, they are dinosaurian holdouts, you could say. Okay. Flying reptiles, kaput, no more flying reptiles. Those pterosaurs we learned about, like Quetzalcoatlus and Pteranodon, right? Swimming reptiles, our ichthyosaurs are gone. The mosasaurs, plesiosaurs, all of those, they are no longer there. Ammonoids, kick the bucket, finally, after hundreds of millions of years of sticking around in the ocean, they're gone, okay? And those rudists, which are those specialized bivalves. Remember, the Cretaceous is the first age when bivalves really took over. Brachiopods took that backseat. Bivalves started taking over, and one of the more popular ones, one of the more fossilized ones that we have all over the place are those rudists, but they only live during the Cretaceous. So they die here. But bivalves in general keep doing well. We'll get to that. All right, so all of this leaves a lot of empty spaces. What do we call those spaces in an ecosystem? Niches. Thank you. A lot of niches are left vacant. What's going to rise up to fill it? Because remember, they don't stay vacant for long. When there's available living space, things are going to go fill it. Okay, we call that an adaptive radiation. Thank you. That's an adaptive radiation, always follows an extinction without fail. Things that the survivors are going to spread out, and they're going to diversify, and they're going to fill in those niches, okay? Taking on new body forms over time. All right, so mammals, mollusks, okay? So a lot more of our modern types of mollusks that we'll see, distributions of modern-looking oysters and things like that, okay? Teleost fish, which are the type of fish that are all over our oceans today, okay? Scleractinian corals. You saw this in a lab. Hexacorals have been the dominant coral in our reefs up until this point. Scleractinian corals take over, and we'll talk about why here in just a minute. All right, so when you're looking at life forms as you have them today, hi, I am a Jedi to honor May the 4th.
Jedi?
Yes.
I thought you said graduate.
Yeah,
This is a graduation robe. But it's, it's also graduation day. The first graduation ceremony's tonight.
What's today?
Yeah. We have graduation ceremonies all week. I have to be at
I know that.
9 ceremonies. Yep, first one's today. Yep. Anyways, yeah, graduation robe with a lightsaber, because it's May the 4th. All right, so where was I? Right, okay, so when you look at a landscape in the Paleogene, when you're looking at the ecosystems, you're going to be seeing things that look generally similar to what you would see today. You'll see things that kind of look like elephants or rhinos. You'll see things that kind of look like lions. You'll see things that kind of look like horses. Because the mammals that rise up and fill those niches start occupying the same, those same spaces that were occupied by dinosaurs. And those spaces are still true today, okay? So we see things start to take on the ancestral shape of what they're going to look like today. All right, so it would look a little off. It would look like if Pablo Picasso painted, an African landscape with animals, but still recognizable, right? Maybe like Earth separated by a few degrees of evolution, if you think of it like that, okay? All right, now, remember I told you how many tiny little animals were living in the ocean during the Cretaceous? Having a mouthful of seawater would be like having the nutritional value of soup, right? Just so many living things, so much organic matter in that water. Of all of those things, all of those foraminiferans that were filling the oceans, only 3 species survived the Cretaceous extinction. Now, I say that with the same caveat that I say with every other extinction. 3 species we know of. Why do I keep pushing that home? Do you remember this? Our knowledge of the past and of what lived is based on what? Yes, the fossils we find. Is the fossil record perfect? It can't be, because it's based entirely on the conditions at the time that the things were buried. Without the right conditions, nothing gets fossilized. Nothing gets fossilized, there's no evidence that we have now that it ever existed in the first place. With the hundreds of thousands of fossils that we have found of different species through time, how many more must have existed that we don't have any evidence for, right? Always bear that in mind. So when I say only 3 species of foraminiferans survived the Cretaceous extinction, that's 3 we know of. But that's still, like, foraminiferans came this close to being kaput, right? They almost didn't come back. But they did. They actually recovered pretty dang quick, and now we're back to having thousands of different species in the oceans today, okay? Foraminiferans, very common in the oceans today. All right, now, there's a big change that we see in our reef systems. I mentioned earlier that we see a transition from those traditional hexacorals. Well, scleractinian corals take over from this point. Now, scleractinian corals are evolutionary descendants of hexacorals. There's absolute shared ancestry there. The big difference, or the reason why hexacorals seem to suffer so much from this extinction, we think is because of a symbiotic relationship that they had, okay? Now, corals, many species of corals, will actually have this symbiotic relationship with algae. They will allow algae to grow within their colonies, the coral colonies, okay? And the algae will actually assist them in things like digesting their food. So the coral will catch the food, and the algae that lives inside of their system will digest it. Very similar to the same sort of symbiosis that we have, right? Have you guys heard of your the bacteria that live inside your gut? You know about your gut biome? We each have colonies of bacteria living inside of our stomachs, and they assist with digestion. This is actually the reason why you produce gas. No one likes talking about flatulence, right? That's not something we talk about in polite conversation. Well, guess what? This is a science class. We don't avoid those sort of things, okay? Why do we pass gas? We produce methane and other gases as a byproduct of the bacteria in your gut processing your food. That gas is their byproduct. Without that bacteria, you cannot process your food as well. This is actually why prebiotics are such a big thing. Prebiotic bacteria, when you eat a yogurt, it'll say prebiotics in there. When you have like a health drink, it'll say loaded with prebiotics. What does that mean? It's either nutrition for that bacteria or a new dose of that specific strain of bacteria you are introducing to your gut to keep it nice and healthy, okay? Because without a healthy gut biome, you will not be able to process food well, and that leads to a whole bunch of health conditions, okay? So we have that symbiotic relationship. Guess what? So do coral. They have a symbiotic relationship with their own thing, with the species of algae. Now, we think the reason why the hexacorals weren't able to keep up after this extinction is because for a while we see them kind of hanging on in the fossil record, and then they kind of peter away after the main extinction. And we think it's because while they didn't die from the extinction events, the changes that came to the environment, negatively affected the algae that they had that symbiosis with. So if the algae dies, the populations of corals slowly die off. Eventually, we do see it come back later on in the Paleogene with scleractinian corals. We think it's because they formed a symbiotic relationship with a different type of algae, right? Which we see that they have today, okay? All right, so our big swimming super predator reptiles are gone. The mosasaurs, gone. Plesiosaurs, they're gone, right? What fills that niche? Mammals. Just like they do on land, mammals fill the niches in the seas too, okay? Whales. We see whales show up, and whales, they get really big. Whales back then do not look like whales do now, okay? We have a few toothed whales today, but most of our whales are pretty gentle, you know, like humpbacks, right whales, baleen whales, blue whales, right? Fairly gentle giant sort of things. We have a few very fierce, toothy whales, though. Do you know what those are? Orcas. What else? Oh, yeah, there's more. Huh? Belugas. Any others? Can anyone think of a whale? Narwhals, yep. Okay, what else? Should I give you another clue? Do we like the clue thing? Hold on, let me get my camera. Dolphins, yeah, dolphins and porpoises. Yes, they are whales. Yep, they're in the same family.
Because they always separate them.
Right. Well, they're much closer in relation to killer whales like orcas and belugas and such than they are to like humpback whales, right? So what I'm saying here is we've got these toothy whales and we've got the baleen straining whales, okay? Which I'm separating to two separate groups, but they come from the same ancestry. These whales that developed during the Paleogene, okay? There's also sperm whales. Do you guys know what sperm whales are? Very aggressive. You ever seen Moby Dick or read, you do know the story of Moby Dick? No? Moby Dick is a story written by, is it Herman Melville? Who wrote Moby Dick? No, it wasn't it was some guy, right? Oh man, I want to say Herman Melville. Someone looking this up for me? Is Herman Melville? Ah, man, I'm good. Okay, so it's a book written by him about a whaling ship, because they used to hunt whales for their oil, because that's how they used to, fuel cars and lamps and stuff. They would kill whales, take their fat, and reduce it to oil. Whale oil was what people used before they discovered oil in the ground. Okay, so that's why most of the whales on our planet are extinct or endangered today, because hundreds of years ago they would hunt the whales for oil instead of drilling in the ground because they hadn't discovered that yet. How did you find out you could, eat a monkey? I don't know. You just try it, right? Think about how many people have lived on this planet and tried everything out. How do people know certain berries are poisonous and certain ones aren't? Someone had to eat it and die first. Yeah, exactly. Who figured out you could milk a cow for the first time, right? What a weirdo that was. And then they realized, oh wait, no, this we could use that, right? We'll actually talk about that in a little bit. We can talk about milk if you like. Okay, but yeah, so sperm whales, extremely aggressive. The story of Moby Dick is about a whaling ship that chases down this big white sperm whale. And eventually, like the sperm whale, spoilers, I guess, if you haven't read this book that's 200 years old. But he actually ends up destroying the whaling ship and killing just about everyone because he's such an aggressive whale. Sperm whales have had a record of being extremely aggressive. They can also go super deep. They can dive miles underwater. They can go deeper than most human submarines have been able to go until recent decades. They're fascinating species, but they are endangered because they were hunted almost to extinction by the whaling companies. Okay, but we do have a few toothed whales left. But during this time, that was all there were. Gigantic 60, 70, 80, 90 foot. I said 60, 70. Don't get started with me, okay? Whales, okay? And they were super predators. They were chomping down on the sharks, not vice versa. Okay? Now, eventually, we do see some very, very large sharks show up on the scene. Everyone knows the infamous Megalodon, right? Okay? Megalodon was definitely real. I have a real Megalodon tooth if you want to hold it. I think it's actually, is it over there? Where did I put it? Oh, it's right here. This is a real, genuine Megalodon tooth.
That's cool.
Yep. I'll show it in front of the camera here in a second, and then I'll pass it around the room. That is a Megalodon tooth right there. This is my smallest one, actually. I have one more in my display case out by my office that's the size of my hand. Go take a look at that. Camera, you need to focus on me. All right, so I'll go ahead and pass that around. All right, now, Megalodons haven't shown up quite yet. We're not there, but sharks are, they are diversifying. They're also filling those niches left vacant by the reptiles, okay? So whales and sharks compete with each other here on out. And you can kind of see right here the evolutionary path that we go from these rodent-looking animals, right, during the Mesozoic with the dinosaurs. to, okay, I'm going to go for a little swim every now and then, to I have like they've got like this beaver tail and webbed feet, and then the transition into these kind of fat-looking porpoise things, and then we're into these mega super predatory whales, and then we go into the two different types of whales we have today, the straining ones, the ones that have strainers in their mouths, and then the toothed whales like dolphins and orcas and sperm whales and such, which are the two groups of whales that we have today. All right, transitioning a little bit, we're going to move on land and we're going to talk about plants. We had a couple of big things happen to plants in the Cretaceous. What was the big one that happened? What was the major big development within plant life during the Cretaceous? No, we already had seeds, but there was a difference. There was a change to them. Yeah, double fertilization. You have the seeds that are the actual seed, and then you have another set of seeds that grow into the fruit around the first set, right? So that double fertilization gives a little bit more protection and a little more burst of nutrition to those seeds when that fruit falls off the tree, rolls away, incorporates into the ground, right? So you start growing your seeds in a matter of weeks instead of a matter of months, like you do with gymnosperms, where they need to slowly, as they move into the ground, they slowly accumulate the nutrition that they need to start growing. The fruit around the trees or around the seeds allows it to start growing faster, okay? So angiosperms, okay? We see the development of those angiosperms. Now, one of the angiosperms that shows up at the end of the Cretaceous, middle to the end of the Cretaceous, but is not widespread yet until the Paleogene, is grass. Remember how I told you before, through a lot of history, there was no grass. Wherever today you would see grass, there were ferns. Well, shortly before the extinction of the dinosaurs, grass shows up on the scene. Do you know that grass is an angiosperm? It is a flowering plant. Some different types of grass you may not realize are grass, rice. Rice is grass. Okay. Bamboo. Bamboo is also a species of grass. Extremely fast growing. There are some species of grass, there are some species of bamboo, I should say, that can grow 6 to 8 inches a day. Yes. Remarkably disturbing fact here, that was actually during World War II. That was a torture technique that was used in Japan, in the Pacific Islands, was putting prisoners of war on top of bamboo and letting it grow through their bodies.
I think I've heard of that.
Yep. It was a brutal war. Okay. All right. So, flowering plants, we're seeing them moving out. They're becoming very popular, but not nearly as dominant as we will see later on, and of course today. Okay. Our grass still hasn't become as accustomed to drier climates. It's kind of following through that same pattern that all plants do, where they need to start off somewhere wet and then they diversify and they become more adapted to colder, drier climates. Okay, but it's still pretty well restricted to the wetter areas. Okay, and then our mammals. Let's see what happens here. Here's our Jurassic, right? We see our mammals during the Jurassic and the Cretaceous are for the most part these small little rodent-looking things, not actual rodents. Actual rodents, let's see, they don't show up until right here, okay? This is our rodent group right there. But what we have a lot of during the Cretaceous are called multituberculates, okay? This group, which look very much like rodents. Imagine if a rat and a beaver had some kind of like weird hybrid with each other. That's what multituberculates looked like. I'll show you a closer picture, well, an artist rendition of one here in a little bit. But multituberculates were the most common type of mammal during the Cretaceous. We have so many fossils of them. Relatively few of everything else. But here, moving into the Paleogene, they are still extremely successful. But moving on past the Paleogene, which we will here in just a minute, you're going to see that they start to taper off. Watch what happens as multituberculates start to taper off. Everything else starts to increase. In particular, our rodents start becoming very successful as the multituberculates start to die off. Oh yeah, sure, thank you. So, why do you suppose we see that pattern here? The other mammals were able to do something. Adapt. Right. They were able to adapt to the conditions while the multituberculates were not, or were not able to fast enough. And so the multituberculates we see will die off while everything else becomes successful in their absence. We'll talk more about that here in just a minute. During the Paleogene, we see a diversification of those few groups of mammals to about 100 different families, which is approximately the same number that we have today. Okay, some have gone extinct, some have shown up since the Paleogene, but approximately 100, which is the neighborhood of the number that we have today. During the Paleogene, ancestral horses were the size of house cats. Yeah, it's weird to think of it like that way, huh? They also didn't have the one hoof, not quite yet. That comes up here in just a minute. And then I mentioned this statistic earlier in the course during Module 2 when I was talking about how quickly life can diversify after an extinction. Okay? It only took 12 million years after the extinction of the dinosaurs for those little rodent-looking things to adapt to all the different environments to the point where we have whales in the ocean and bats flying in the sky. Only 12 million years we go from rodents to bats and whales. That is a remarkable timeline for adaptation. Okay? Now, let's hesitate on that point for a second there. What advantages do mammals have going for them that the animals in the past did not have or did not have as much of? That we are aware of anyway. What's one thing that mammals have that, say, reptiles in general do not? We do have fur. That is a good point. It provides some protection, but for most mammals, the fur that they have isn't a huge protection to the elements, right? Like for you and me, our hair doesn't really protect us from a snowstorm. A snowstorm, like dog's fur doesn't protect it too much from, drowning, right? So there are certain conditions where it's slightly favorable, but in general, having fur is a characteristic of a mammal without being what I would describe as being a very important change. Warm-blooded. What advantage does an organism have from being warm-blooded? Right. Like if you put us up against a reptile, my reptiles have to sun themselves for a couple hours a day before they can do anything, right? You and I, we don't have to do that. We get up out of bed, we drink a cup of water, right? Some people have some coffee. Some people eat an egg or two or a bowl of cereal, and we just get right to it. You can get right to it. You don't even have to eat anything. You do eventually. Some people just skip breakfast. We have the ability to generate our own energy, right, through our metabolism. Not only that, we have the ability to store fat for later and burn it whenever we are in an absence of ready energy like food. We have some distinct advantages being mammals because of our metabolism type. So, this gives us a lot more opportunity to put energy into things like adapting to our environments efficiently. All right? So, 12 million years after the extinction of the dinosaurs, bats in the sky, whales in the ocean. Incredible. All right. Now, for our mammals on land, we start to see some of them split into a couple of different groups. Interestingly enough, we separate them by the number of toes that they have. We call these ungulates. Okay? That just is a description of their feet. Okay? They undulate. Undulate is the word for walking, right? I undulate or I move across the surface of something, right? But ungulate, that's a description of their toes, all right? So we have even-toed ungulates, which includes things like camels, right? Which have 2 toes. Bison, pigs, right? Then we have odd-toed ungulates. Horses have 1. Tapirs, rhinos, 3. Right? You ever notice that rhinos have 3 toes? Okay, so those are even-toed ungulates and odd-toed ungulates. That's how we just separate them from each other, differentiate them. And that starts here in the Paleogene. The first elephant ancestors show up on the scene. This is Moeritherium. When you look at that, do you think elephant? It has some elephantine characteristics, right? The body, if I just separated the head, right? If I just with my lightsaber off that head, and you look at the body, you might think, oh yeah, that's kind of like an elephant. But when you look at the head, that doesn't really scream elephant. Kind of looks like a rat pig, right? The ears, those don't really say elephant either. But this is the first elephantine ancestor, okay? Moeritherium. Now, later on, we're going to see this transition to this. This is Paleomastodon. You can absolutely see how that is a kind of a middle-of-the-road transition towards elephants, right? That little snubby nose there has turned into a short trunk. These teeth, which, by the way, this isn't a carnivore. What were those teeth used for? Digging through the mud, looking for roots, okay? It would rip through the mud on the side of a bank looking for yummy roots to eat, right? Those have lengthened out into what you can clearly see are going to become tusks, right? The body size has increased. Look at the ears. They go from this kind of mouse-like ear to this sort of droopy half-elephant ear that you can see there, okay? We see these traits, these characteristics becoming more exaggerated, like the trunk, like the tusks, like the ears, and the body size, because they are positive for that organism and the environment that it lives in, ultimately leading to what we have today in the actual elephant. All right, rodents do show up here in a little bit, but for now, what we see are multituberculates at the beginning of the Paleogene. Towards the end, we see the rodents, and the multituberculates start to die off. Why would our multituberculates, like this guy, not be able to keep up with rodents? They look about the same. They occupy the same niches. Multituberculates were actually a little bigger, huh? Their speed? It's hard to tell things like speed. Which was faster, a rodent or multituberculate? Hard to tell without musculature. All we have are bones.
That's what I was saying, like, the rodents are
Smaller,
smaller.
so speedier, possibly. Some were smaller, some were bigger. Any other ideas? What about food availability? They both eat the same foods. They live in the same places. So there's already competition there. Rodents got one advantage over multituberculates, though. Multituberculate teeth stop growing. They grow, and then they would wear down. The more you eat, the more you wear your teeth down. The more your teeth wear down, the smaller they get. The smaller they get, the less you are going to be able to eat, right? And eventually you die. But with rodents, and this is true today, by the way, rodents continuously grow their teeth. Their teeth never stop growing. That's why rodents have zero hesitation. Rats can chew through metal and concrete. Did you know that? Yeah. They will chew through just about anything given enough time because their teeth always grow back. Okay? It's just unfair. Well, it was, because the multituberculates couldn't keep up. They died off, right? While their individuals and their species would reach a certain age, or their teeth would wear down to a certain point and they would die of starvation, all of a sudden you get rodents that have a longer lifespan and a healthier lifespan from being able to eat for longer. Okay? And so the rodent population outgrew the multituberculate population and they went extinct. Okay? This is Paracetherium. This is the tallest land mammal, I should say, not land animal. It's not a titanosaur. But this is the largest mammal on land to ever exist. They stood about 20 feet tall and 25 feet long. When you look at that, can you tell me what you think its modern-day descendant is? Giraffe? It's very giraffe-y, isn't it? It's actually not. This is the ancestor of the rhino. Yeah, isn't that weird? Yeah, there are definitely some traits. Now that I've said it, you can see some of them. Look at the armored skin folds you can see on the legs, right? The ears, theirs are very rhino-like ears. The head, even, is very rhino-ish, just minus the horns. So what happened here? Well, at some point down the road, it became more favorable to have a shorter body size, right? Smaller body size, tankier, less tall. and the horns showed up. Otherwise, you can look at that, and it's just a matter of proportions and adding the horns, and you can see a rhino in it. Now, did this occupy the same niche that giraffes do today? Yes. And remember that co-evolution concept we talked about, where the same traits are positive in the same niches, no matter where. That's why the animals in Australia look very similar to the animals in North America, even though they're different groups of mammals, marsupials and placentals, because they occupy the same niches, just in two different geographies. The same traits are positive. And so the same traits that were positive for these guys to have this body shape are true for giraffes today. Okay? Our predatory land mammals, we don't have the distinct different types of predators that we do today. We don't have lions and tigers and bears, oh my. Okay? All of those are kind of grouped into a couple of different broad categories, mesonychids and creodonts, okay, which look very similar to each other. These are, remember, these are just artist representations. These different groups, like mesonychids and creodonts, are going to eventually split off and turn into cats and dogs. Wolves, I should say, right? Dogs are a creation of humans, but you know what I'm talking about, okay? Eventually, modern carnivorous mammals are going to come off of these guys. Right now, you can see there are definitely cat-like characteristics and dog-like characteristics in both of them, right? All right, so while mammals are obviously the dominant groups on land and sea thus far, we've talked about in the Paleogene, in the beginning of the Paleogene, there was the possibility that it wouldn't go that way. Do you remember at the beginning of the Triassic, I mentioned both mammals and dinosaurs showed up approximately at the same time, but dinosaurs had a 2 or 3 million year head start, right? Well, birds tried real hard to fill the niches left by their dinosaur cousins, okay? But they weren't able to keep up quite as well with evolution as the mammals. There were a couple of birds that did really well, okay? For example, Diatrema, like this. That's a bird eating a horse, right? Remember, the horses were the size of house cats at this point in time. But there were birds that essentially started filling the same niches left behind as the carnivorous dinosaurs. What's the problem here, though? The mammals could evolve faster, right? We have that metabolistic advantage as well as a few other things, right? So while the birds, some of them got big, and we do still have big birds like this, right? We do have large carnivorous birds, ostriches, emus, cassowaries. Have you guys ever seen a cassowary? Those are the scariest birds you'll ever see in your life. And they stand about 7 feet tall, and they still have feet like that. They can gut you. They've killed people, right? The cassowary birds. Mammals ended up winning that particular arms race. So while birds still stayed very successful, they did not rise up and fill the space left by the dinosaurs. The mammals ended up doing that even so. All right, primates. The first primate showed up at 55 million years ago. And that is an artist representation of what it would have looked like. It's tiny little, like fit in a teacup sized primate, monkey, right there. Another evolutionary change from those rodent-like animals that we saw during the dinosaur time. So some of them, they started flying. Some of them started swimming. Some of them got longer limbs, longer fingers, prehensile tails, and took to the trees. And these become our primates. All right, moving on towards climate and tectonic information. During the Paleocene and the Eocene, which are the first two time periods here, actually, let me go back a little bit and show you this, because I think I may have accidentally skipped over this part. Okay, so our Paleogene is separated into three groups: Paleocene, Eocene, and Oligocene, okay? Right there, Paleocene, Eocene, Oligocene. So now going back to where we were, during the Paleocene and the Eocene, which are the first two time periods. So here's the Paleocene, the Eocene right here. There's a lot of warming. It gets real hot, okay? It's get its hottest right here in the early Eocene. So these are delta oxygen 18 values, okay, which we correspond to temperature, and they also correspond to precipitation rates, okay. All right, so we see a massive spike all of a sudden. So there's this obvious, definite climb in temperature, and then a massive spike right there in temperature. What might do that? Well, that's a very good question. One we spent a long time trying to figure out. Best as we can figure, what probably happened was, as the oceans were warming up and the sea levels were, there were parts of the deep seabed that were getting pushed up by tectonics closer to the surface. These things called methane hydrate crystals dissolved. Methane hydrate crystals it's when methane enters the ocean and then through one process or another goes really deep in the ocean and then forms a crystal because of how cold it is, okay? Think of it as solid methane down at the bottom of the ocean. And that piles up for hundreds of millions of years. Well, methane is a greenhouse gas, and it's getting stored at the bottom of the ocean by this natural chemical process. What happens if I take that ocean bottom and I lift it up closer to the surface through tectonics, and my sea level and my oceans are heating up because of the normal increase in temperature here? Well, my methane hydrate crystals, they turn into a gas again. That gas comes up, bubbles up out of the ocean, and all of a sudden we have this massive influx of greenhouse gases into our atmosphere, which is going to do what to our temperature? Spike it. So we see this big old spike. We call it the Paleo-Eocene warming event, or climactic optimum, okay? Well, that's the event. Then the climactic optimum comes after that. Okay, so we get this big old spike, a little bit of recovery, and then general temperatures around the world get real high again. And then we see a drop-off as those greenhouse gases get reabsorbed into the system. The trees do their thing, right? One thing leads to another. We go into a natural cooling trend, okay? Then we see another pop, big spike like that, right here in the Middle Eocene. We call it the Middle Eocene climactic optimum. And then it drops back down. And then right here, look at this massive drop-off. Boom! Big temperature drop right there. This is what we call the Ice Age, okay? That was the beginning of our modern Ice Age, because remember, we're still technically in it. An Ice Age is a period of time when we have ice at both poles. We still have ice at both poles, and we have ever since this point in time, it's about 35 million years ago now, okay? So we are still technically in this particular Ice Age. We just go back and forth between glacial maximums and global warming events, okay? So, big drop-off, ice forms at the poles, stays at the poles, okay? And then we move into the Oligocene. All right, so this is where we are at in the Middle Eocene. So the middle of the Paleogene, it looks like modern-day Earth. What's the big difference here? We have this big shallow sea in the middle of Europe and Middle East. Africa has not come up close enough over there to make the mountain range here and push the Alps and the rest of Europe out of the oceans. Okay. North America looks very similar to what it is, except Florida doesn't exist. South America does not have any connection to North America right now. Antarctica is hanging out where it should be. Australia is still just barely close to Antarctica, right? That would be a fairly short boat ride from Tasmania over to Antarctica still, okay? Australia is going to work its way up here in a little bit. India has not finished colliding over here yet. During this time, it starts that collision. During the Paleogene, it starts that collision. The Himalayas are just now starting to form up here. But India itself, the continent, is still separated by a strip of ocean right there. Madagascar is where it should be. It broke off from India during the Cretaceous. All right. The Laramide orogeny, which is Cordilleran, so west coast, okay. This is what happened. We get a whole bunch of volcanic activity out here, okay, plus all the thrusting of material as the Pacific plate shoves into North America. We're still thrusting all that material. So there's volcanic activity plus thrusting material out here, and that finishes off making our Rocky Mountains. We've had the foundations of the Rocky Mountains already laid down. Okay, we've had some highlands deposited there by the thrusting during the Mesozoic. This finishes off making our modern day Rocky Mountain range that we've got here. During this time, we have the Tejas Cratonic sequence. So, as sea levels were very high before the Oligocene, this lasted until the Oligocene, because during the Oligocene, right, sea levels dropped during an ice age, right? So all the way from the beginning of the Paleocene up to the Oligocene is this Cratonic sequence. Sea levels very high because of high temperatures. All of this Mississippi River embayment here, all the way up to Memphis, Tennessee, and a little past it, almost to Kentucky, was flooded by the ocean. So wherever you see all of this that you see here, all this river, was ocean. Okay? The ocean was all the way up here. And a whole bunch of ocean sediment was deposited. A whole bunch of sand was put there. Okay? A little bit of history here. This is extremely sandy area, making it difficult to farm. Okay? And so in past American history, a lot of this farmland was sold or given away for very cheap to people, and there's a very long record of people farming out here, but it was never easy for them to transition that soil to be able to be farmable, okay? Because of the nature of this geological fact of the Tejas Cratonic sequence making it so sandy. All right. The Rio Grande Rift formed during the Paleogene. Okay, in the Oligocene, there was a lot of volcanic activity out here where we are now. Okay, why the Rio Grande Rift? That sounds familiar, right? Well, that's because it's right here. This is the Rio Grande River, the course of the Rio Grande River. That volcanism occurred out here, making those mountains, the San Juan Mountains, right? But this river is flowing through what is called the Rio Grande Rift. That rift exists because there is underneath of us, and I say us, we're actually over here, right? But it's not too far away. It's about 200, 250 kilometers, right, to get to the river that way. But this rift is forming here because the crust is thinning out. Why is it thinning out? Because a divergent plate boundary is forming right there. There are convection cells under the North American plate doing this now, stretching it out. As it stretches, it rifts. As it rifts, the valley is formed and the river runs through it. Eventually, if it continues on this course, there is going to be an extension of the Gulf of Mexico up into North America along where the rift is right now. The Gulf is going to flood in once that rifts out shallow enough. Okay? Exactly what's happening with the Red Sea separating Saudi Arabia from Africa right now. 36 million years ago, there was a giant asteroid impact, not enough to make a massive worldwide extinction, but definitely noticeable in the area around North America. Okay, it impacted right here where modern-day Chesapeake Bay is, and this is actually why Chesapeake Bay exists in the first place. So this asteroid impacted, made a big old crater, which, look at this. You guys see this weird spike right here? This is our impact crater, right? This is the rock that was there before. So this got metamorphosed, it got melted, this asteroid impacted. What is that weird spike there? Think about this question for a second. What happens if I drop a little rock into some water? Slow motion, think about it. The rock hits the water. It makes a sort of crater in the water, right? The rock passes into the water, and then right in the middle, what happens? There's a little bloop of water that comes up. And because it occupies the space, it fills in the space that was left by that rock so quickly that it kind of bloops upward. That's a technical term, by the way. Okay? You can quote me on that. It bloops. Yeah, the asteroid was the rock. It immediately melted this part of the crust that it impacted. All that melted rock filled in the space left behind and went bloop upward and immediately solidified into that bloop. We are seeing the solid bloop from that. I'm sure there's an actual name for that, but I don't know what it is. Okay? Someone has probably made a name for the little bloop of water that comes up from a splash. I don't know what it is. And that filled in with sediment left behind as a result of that impact. It filled in with all of the shatter cone, breccia, and everything that got washed into it. Now, what does that have to do with modern day Chesapeake Bay? Well, all the layers of sedimentary rock that got deposited on top of that crater, as that breccia has continued to settle and fill in the empty spaces inside, the layers of rock on top of it fault down into it. And all of those faults have caused these slump blocks and valleys here, okay? And that filled in with ocean water, making Chesapeake Bay. I have a goal to drink a gallon of water every day. I'm trying to improve my hydration. Any questions about the Paleogene? Okay. Then let's move on to the Neogene. If it would like to open for me. Not responding. There we go. All right. The Neogene is composed of the Miocene, Pliocene, and Pleistocene epochs. Okay. The Pleistocene, by the way, is the end of the Pleistocene is where the end of the last glacial maximum was 11,700 years ago. So we're going up until that point in the Neogene here. All right, so that's what we're working with. Whales during the Neogene start looking a lot more like what we've got today. Less gigantic, toothy, 80-foot predators, like very similar to the mosasaurs like what we saw before. More modern whale-ish. Okay, we see a differentiation of toothed whales from baleen whales. Okay, so our straining whales, they evolve away from teeth and towards having row upon row upon row upon row upon row of tiny, tiny, thin little teeth, or very, very thick hairs, however you want to think about it, okay, on the sides of their teeth. So what do? They open up their mouth, take a gigantic mouthful of seawater, and then close their mouth and use the massive tongue at the back of their throat to push that water back out through their mouth. And that leaves all the nice, yummy little fish and krill on the inside of their mouth, which they then lick up and swallow on the inside of their mouth. Okay? So they're more of a passive feeder than they are a hunter. I mean, they'll follow the patterns of the migration patterns of krill and stuff like that, but they are not nearly as aggressive hunters as their ancestors used to be. Okay? And as some whales still are, the dolphins and the orcas, those are still extremely aggressive hunters, right? It was advantageous. Let me ask you this. This is actually a good question. Why did they evolve to be like that? Does it cost more energy for me to hunt a sheep or to eat mushrooms and plants and stuff like that? Right. Eating things that can't run away from you or can't run away as fast costs less energy. It's far more energy efficient for me to hunt and eat turtles than it is for me to hunt and eat kangaroos, right? Or lions, or horses, or antelope, or anything that can run quickly. Now, those things have a higher energy return, but they cost more energy to get. So, some organisms have evolved to subsist off of the things that are easier to hunt. And so that's an example here. The baleen whales kind of just swim through the oceans and passively swallow water and squirt the water out and eat whatever that gets stuck in their baleen, in their strainers, along the way. Costs less energy. It's also why those whales tend to be the bigger ones. Okay, the largest animal on Earth right now, do you know what that is? Nope. Blue whale. The blue whale can get 120 feet long. It doesn't hunt its prey. It's a baleen whale. All it has to do is float through the water and just live and strain its food out, right? Which is what made it such easy prey for humans that wanted its blubber for oil, right? That's why they're mostly extinct. They're very endangered. So yeah, just different evolutionary paths. It depends on what's favorable for that species in that environment. Good question. Okay, plants. During the Oligocene, it gets really cold, right? We're in that ice age. Animals and plants need to adapt to that. So, a new different type of plant shows up. We call these herbs. You guys know what herbs are? There are herbs that are medicinal. When I say herb, most people think cooking, right? Oregano, basil, thyme, sage, whatever, right? Those are culinary herbs. But the actual biological type of plant called an herb has a few characteristics. They are non-woody, okay? They are flowering plants, and they need to die off every year. The same plant doesn't come back. Okay? You need to grow them from new different seeds that were dropped by the previous plant. Okay? Now, this came by as a byproduct of how cold it was getting. These are much more survivable in cold conditions. Grasses, by the way, they also start spreading out at this point because they have adapted to the cold. And they become the basis of the food chain, at the bottom of the food chain for a lot of herbivorous animals. We'll see that here in a minute. Matter of fact, they become such a foundational food source for so many herbivorous animals, mammals in particular, that grasses evolve this thing called phytoliths. Remember, evolution has nothing to do with thought. It has to do with random mutations that are either positive or not. Had this adaptation come up a couple million years earlier, it would have come and gone and never made a difference. But what happened here is there was a random mutation in the grasses to start growing what we call phytoliths, which are tiny little silica nodules inside of them in their tissues, okay, in the grass stems. So if I'm an antelope and I'm going through and I'm eating the grass, and the grass has these little silica nodules in it, my teeth are going to wear down and grind down faster than they would normally, and I'm going to die off pretty young from eating it. So the populations of animals that would prefer to eat that silica nodule grass, the phytolithic grass, die off. And the grass is preserved. And this is why it becomes a positive mutation. The populations of phytolithic grass become more successful. And it spreads out. And it becomes a whole thing. As a matter of fact, it becomes a big problem for the herbivorous animals later on, the grazing animals. We'll see what happens there in a little bit. We see a different type of photosynthesis show up in plants. Okay, so up until this point, photosynthesis in plants has mostly been what we call a variation called C3. C3 plants, like elm and many other trees, they'll take in carbon dioxide. It'll go through a cycle that breaks the carbon off from the oxygen. It'll expel the oxygen and byproduct water and keep the carbon to continue building its tissues. C4 plants do the same thing, but very much more efficiently. Okay, they do it a lot more efficiently. So there's a few extra cells involved here. And C4 plants start becoming extremely successful during this time because they can take on the colder conditions a little bit better. Okay, an example of a C4 plant is corn. Okay, corn is a very versatile plant. It grows in a lot of different places. Okay, for this reason. All right, so as plants, in particular grasses, develop these phytoliths, animal populations start to suffer because they can't eat that basic food source, those grasses that they need to, until there is an adaptation that responds well to that, right? That evolutionary arms race we talked about before. So when the plants did this thing, when the grasses did this thing, animals suffered until they did a thing that could match it. In this case, what happened? Teeth. It's the teeth. If the problem is that the teeth wear away faster, what's the answer? More teeth. You can do that a couple of different ways. The rodents, continuously growing teeth. They already had that problem in the bag. There are some animals that will shed their teeth and grow new ones. Can you think of any? Sharks do that constantly throughout their lives. That wasn't really in response to the grass thing. Sharks don't eat grass, but that's a good example. Can you think of any other animals that shed their teeth and grow a new set? Humans. Y'all lost your baby teeth, right? There are some people that don't actually lose their baby teeth. Did you know that? They have a mutation that prevents their baby teeth from falling out. It's weird. It's interesting. Anyways, so yeah, that happens to us. But another answer? Bigger teeth. Longer teeth. So we see these animals that rely on eating these grasses for survival, we see their teeth grow longer and longer and longer. The ones that have the longest teeth as a mutation are the ones that have the longest lifespan because they can keep eating the grasses with phytoliths in them. Okay? So that's their answer to the situation. All right, climate-wise, this is what we're seeing in the distribution. So this is where we are now. This is general climate and environment now. Ice up here, ice way down here. It doesn't show Antarctica on this, but ice would be way down here on this map, okay? You can see our distribution of deserts. You can see our rainforests, right? We have big parts of rainforest up here, rainforest in Central Africa, rainforest over here, right? During the last glacial maximum, this is what it would look like. Very small amounts of rainforest in South America. Extremely small pockets of rainforest in Africa. Some rainforest out here in Indonesia, but the ocean levels are small enough that Indonesia is actually an extension of Southeast Asia. Okay? Much less rainforest in this condition. Why? Not because it's hot, but because the amount of available water is so much smaller. When it's cold, you get less water and you get more snow, but the snow tends to hang out up here and down here, not out here. It doesn't snow in the equator, but you also don't get as much rain. So rainforests aren't as extensive. That's going to be very important later on. How do we know all of this stuff? Well, once we get into layers of rock that are much more recent, a new type of paleontology is introduced here. We call it palynology. Palynology is becoming very popular. It's very effective. It's the study of looking at microscopic samples of pollen, fossils of pollen. Yeah, how crazy is it that we have gone to the point where our technology can pick out pollen fossils in rock? It's fascinating. How do you look? Well, we know what modern-day pollens look like, and so we can look through a microscope, like an electron scanning microscope at a layer of rock, and we can look at, okay, there's a pollen sample right there, there's a pollen right there, there's pollen right there. These look like pine tree pollen. These look like apple tree pollen, right? And so we can make interpretations about environment and what the ecosystems look like by looking at the different types of plants that had their pollen there, right? Without the plant, there wouldn't be pollen. So, and that gets trapped a lot in the waters, like lakes, and then it filters down into the muds at the bottom of the lakes, and that's where we'll get a lot of our pollen fossils from. Now, whenever something happens to any organism on the food chain, there's going to be what we call a cascade effect, okay? This includes any extinction along our food chain and any adaptation on our food chain is going to result in one of these cascade effects. So if my grasses develop phytoliths, then the things that eat the grasses are going to die off or have to adapt, and so on and so forth. Those things die off, then the things that ate those things die off. So when our grasses do a thing, or our herbs do a thing, the stuff that eats those that has to do a thing. And then the things that eat that does a thing. And then the things that eat that do a thing. we often see these effects cascading up or down on our food chain. And that's evident in the fossil record. All right. Our mammals in the Neogene. There's a couple of shifts that we see here. Okay. Odd-toed ungulates, we start to see way less of them. Things like horses, not nearly as many in the fossil record after this point. Our even-toed ungulates, though, become very popular. Lots of different species of what would eventually become things like pigs. Okay, lots of those. Giraffes and elephants, they do very well, especially elephants. Elephants during this time get very, very, very big, very, very, very furry, and we have a name for those. Mammoths and mastodons, right? Cousins to each other. But yeah, the woolly mammoth. This was the day, the age of woolly mammoths being on land. Okay. We also see bears. And by the way, bears used to be real big. If you think grizzly bears or polar bears are big today, you should see cave bear skulls. I've held one before. Okay. So polar bear skulls, they're pretty big. Polar bear skulls are about that big. I've held a cave bear skull that big before. Yeah. They got sketchy. All right? Huh? How tall could they stand? Like floor to ceiling here? Yeah. If they stood up tall? Yeah. Big bears. I mean, polar bears, when they stand up on their hind legs as tall as they can get, they can stand like 8 feet tall. All right. We already talked about the phytoliths. We talked about all of that. All right. All right. The Neogene is extremely important for a very big reason for you and me. I mentioned 55 million years ago is when we see the first primate. Those tiny little teacup-sized, monkey-looking things that would eat insects and berries and stuff. Well, what's happened to them? They have held on somehow, including through this ice age, probably in those rainforested areas at the equator. Okay. But during the Neogene is when primates really start diversifying a lot, from just being monkeys in trees to having different types on land as well. I wonder, give me a second here. I'm going to see if my coworker left my tray of monkey skulls in the next room, which is not something you hear every day. Shoot, they are teaching in there right now. All right, we'll make do with what I've got. That'll work. This will work. This will work. All right, now, as I move into this next section of conversation, I really want to push something home to you all again. I said this at the beginning of both classes, but this tends to be the part of my classes that people find the most polarizing. Oh, where's my camera? Camera's looking at Ivan. Go that way. What, you think they're more charismatic than I am? Come on. Over here. All right. I need to separate you guys. My camera's just, it's attracted to all the aura over there. That's what's happening. All right, here we go. Now, the subject of human evolution is something that people will either find very fascinating, and some people, depending on the way you were raised, will find very polarizing, okay? I'm going to repeat this. This is, again, what I said at the beginning of the class. Nothing that I teach in my class is meant to persuade you or dissuade you from any previously held belief. That includes religious ones. However, this is the science as we understand it. That is what I'm going to teach. This is what I believe. You've been with me for like 16 weeks now at this point. I'm pretty sure you've picked up on the fact that I have my own religious beliefs. But I also do happen to believe in evolution, including this component. I'm happy to have conversations about that outside of a class setting, but we are going to be learning about this. And regardless of your opinions on the subject, this is the science that you will be expected to know for things in, say, our exam. Okay. Now, the subject of primates is fascinating. Are there primates in Africa? Yes, there are. There have been for a long time. We call those old world primates or old world monkeys. Are there primates in South America? Yes, there are. We call those New World monkeys. Now, here's my question for you. How long ago did Africa and South America separate from each other? Was it before the dinosaurs went extinct? Oh yeah, way before then. They've been separated from each other for more than 100 million years. So then why are there monkeys on both continents? If the first primate that we have in the fossil record is 55 million years old. They were connected, but they separated from each other before the dinosaurs even went extinct, before our fossil record for primates. So why are there primates on both continents? Because they what? But how can you fill a niche across an ocean? Do you think that they swam?
No, they had like same type of environment, so they evolved.
The likelihood of primates evolving independently of each other on two separate continents is like infinitesimally small. A land bridge, that is a great idea. Now, during this ice age, during the Oligocene and moving into the Neogene, there was a land bridge. And there is another land bridge that we will see as we go through warm and cold. We will see land bridges appear between, between Russia and Alaska. But here's the problem with that explaining what's going on in South America. The land bridge of Panama didn't show up until a little bit later. Definitely not before 55 million years ago. This is kind of a mystery we're still trying to figure out. Plenty of people have ideas on the matter. There's this fun thing called rafting, right? Where an animal will hitch a ride on a piece of debris and go from one continent to another. We know that this has happened. That's how we have lemurs in Madagascar, right? There are no lemurs left that are live on Africa. They've been extinct on the main continent of Africa for tens of millions of years. Well, I don't know about tens of millions, but at least 10 million years, I believe, right? But they are still alive in Madagascar. We know they evolved in Africa. We know that they are currently alive in Madagascar and extinct in Africa. How'd they get to Madagascar? Essentially a boat, not one they built, but probably there was some big storm and there were lemurs living on a tree that got blown into the ocean, and they just held onto that tree for a few days while the tree got blown to Madagascar across the ocean. We know that this happens. It's in the fossil record. But is it possible that a tree got blown all the way across the central Atlantic? Maybe.
I mean, they were a little bit more connected, right?
They were a little closer, but not much. Are you talking about the finches in the Galapagos Islands? Is that what you're thinking about? Oh, they hitched a ride on a bird? I mean, that's less likely, right? I'm just imagining at this point a lemur like with a saddle on a big old eagle or something, but no, that's less likely. Birds do cross-contaminate, so to speak, across continents. How? They poop out seeds, right? A bird will eat a seed over here, fly to another place, and poop the seed out there, and that seed will plant and grow itself there. That happens all the time. Doesn't really explain the monkeys, though. Okay? Now, there are a couple of options here. Yes, it's entirely possible there was a land bridge at some point, from one part to another part. It's entirely possible as well that something got rafted. It's also entirely possible that our fossil record is incomplete. Ah, there it is again. Any answer or any question, any mystery in the fossil record that we have, we always have to assume we have an incomplete record, and therefore that might be the answer. It's entirely possible that monkeys did exist, or primates, not monkeys, that primates existed before the continents separated. it's entirely possible that what was the point I was going to make here? Before they separated, there was another thing I was going to say. Oh, that's what it was. That there is some sort of convergent evolution there, where you had the same species living on both continents before they separated, and then through some miracle, they ended up evolving with nearly the same types of traits across that vast distance. Okay, that is very possible as well. Statistically small, but possible, right? So there's a couple of different ways that this could be, but what we know for sure is there have been primates on both continents for a very long time. Okay, so regardless, we separate them into Old World monkeys, aka those on Africa, and New World monkeys, aka those in South America. All right, and why this has been the way that it is a subject of much debate and conjecture. Africa has the longest fossil record with them, though, so we're pretty certain that's where the initial appearance and evolution of primates occurred. All right, so this brings us to humans. You and I, are primates. Okay? Humans and chimpanzees and gorillas and every other primate, we are essentially evolutionary cousins. We have characteristics that are so much in common, they cannot be ignored. We don't look like bats. We have a few things in common with bats. We don't look like whales. We have a few things in common with whales. We don't look like lizards. We have a few things in common, less than we do with bats and with whales. We don't look like bacteria, right? We have way more in common with them than we do with, say, a rock. 50% of your DNA is shared with a tree, right? 99% of it is shared with a bat. 99.9% of it is shared with an ape. 99.999% of it is shared between you and me. What makes you and I different is that 0.0001% difference. What makes you and a gorilla different is that 0.01 difference. What makes you and a tree different is that 50% difference. This is the biggest evidence for the concept of evolution here, is how much we have in common with everything else on our world. And the fossil record that shows where things branch off from each other. Okay, so as far as humans go, we are in the superfamily Hominoidea, as are every other monkey and primate that we've got on this world, okay, on our planet. Now, before the Pliocene, we don't have a whole lot of records for primates. Spotty, here and there. Okay, the oldest one I told you about, 55 million years. Again, very possible that they were before that. The actual apes, though, which are the smaller group that we are incorporated into, those begin during the Miocene. We can see that the oldest fossil record is in Africa, and then after Africa crashed into Eurasia, made that land bridge there, they separated and went up into Europe and Asia, and then to the rest of the world from there. I'll talk about this more in detail here in a minute. This is just a general overview, okay? Now, during that point in time, the world is very cold. You remember what I showed you it looked like during the last glacial maximum? It was even worse during the Oligocene. The world is very cold. Those pockets of rainforest that I was showing you on the African continent, that was the only place where something like a primate could survive. Okay? Only a few species of primates survived in those pockets of rainforest that we see in the fossil record, including the infamous Gigantopithecus. Have you heard that one before, that name? Some people call him Bigfoot. Bigfoot, as people refer to him, is commonly shown as being a Gigantopithecus, which have been extinct for a very long time, which is why Bigfoot is, clearly not. If Bigfoot exists whatsoever, which I don't believe. Okay, Gigantopithecus, which you can see here. You can absolutely see characteristics in here that would lead to both things like chimpanzees and gorillas and orangutans, right? It has characteristics of all of those things, and all of those things ultimately branch off from Gigantopithecus. Now, there was at least one other species of ape that survived in this environment, in these tiny little pockets of rainforest as well. Only bits and pieces of bones have been found from it. It's clearly not Gigantopithecus, but we also haven't found enough to verify what else it was or if it's something completely new. Okay? Regardless, only a few species survived in these rainforests through the Miocene extinction.
Have you ever seen the Jungle Book?
Yes. Oh, yeah. You're talking about the big one? Yes, that's supposed to be a Gigantopithecus. Yeah, the big King Louie in the Jungle Book is portrayed as a Gigantopithecus, or a massive orangutan. But, I mean, he's too big to be an actual orangutan, right? But they even, like, that's way too big. The way that they show King Louie, and especially in the new one, way too big to even be a Gigantopithecus, right? All right. After that Miocene extinction, apes branch out from those pockets of rainforest and become much more adaptable. Okay, they start occupying the grasslands. They move into the sparser parts of Africa, and eventually they're going to move out of Africa and up into Europe, like we're going to see here in a little bit. So, this is where we start to see our particular ancestors show up. This is a skull of Sahelanthropus. Sahelanthropus is what you can think of as the missing link. For the longest time, we could not find any way to connect something like this, which is a chimpanzee, to something like this, which is a human. No, these are casts of real skulls, okay? But you can see so clearly what the similarities are. But there's a bridge missing. There's a gap between these. For the longest time, we couldn't figure it out. Sahelanthropus fills that gap. Look at this chimpanzee brow, very prominent brow. Look at the Sahelanthropus, obviously, very prominent brow. Gorillas, same thing. Chimpanzees, orangutans, very prominent brow structures, small craniums for their heads. Very forward-looking. Look how forward the face is on this. It pushes out of the face on this chimpanzee, right? Much less pronounced in Sahelanthropus, almost non-existent in a human. Our faces are pretty flat compared to chimpanzees. Sahelanthropus is halfway between the two. Look at the eye sockets. Here on a chimpanzee, right? Very large, very kind of slanted. Sahelanthropus, flat. On human, flat to our face. Look at the teeth. On a chimpanzee, very large canine structures. On a human, tiny canines, large incisors, molars for chewing. Look at this guy. Large incisors, about the same size as canines. The canines are still very large, but smaller than a chimpanzee, bigger than humans. Transition. Sahelanthropus represents that sort of transition there, okay? Now, after Sahelanthropus, we see these things called Australopithecus. This is an Australopithecus skull. Australopithecus afarensis. 4 million years old. I 3D printed this off of an original cast we made, okay? This is what they look like.
Were those like the first, well, not the first, but like, they had more like human?
Australopithecus looks like this, okay? So here's the skull, right? Right there. Look at those arms. Very, very long. Does anyone's arms here go down to their knees? Hope not. You'd be a chimpanzee pretending to be a person, right? No, they go down to maybe mid-thigh at the longest. These arms go down to their knees. Clearly, these arms were still great for climbing. Look at those long, thin fingers. Clearly, still great for climbing. But look at these bone structures. Look at the hips. Walking upright. No longer on all fours. Capable of climbing in the trees and walking. Okay? Bipedal, that's what we call that, walking like that. Fingers, like the chimpanzees. Ears, like modern day apes. But look at the brain size compared to our chimpanzee friend here. The cranium is increasing. Cranium getting larger. Okay, that means larger brain size. Now, brain size isn't everything. Remember that? Brain to body ratio. We learned about that early on. Brain to body ratio isn't everything. Do you remember what animal has the largest brain to body ratio on Earth? Nope. Ants. If aliens came to Earth today and their only standard for intelligence was who has the biggest brain versus their body, they would go talk to the ants. 25% of an ant's body is taken up by its brain. Yes. So if that's the ratio for intelligence, we are dumb. Ants are smart, right?
They're pretty smart.
They're very intelligent as a hive and very instinctual as an individual. But, I mean, there's nothing that we would describe as having like technology or engineering or any understanding of science as we perceive them having anyway, right? So brain-to-body ratio, clearly, at least by our definition, is not the way to go. But their brains are getting bigger. And with bigger brains comes bigger capability, okay? So, this is Australopithecus. After them, because remember, they're 4 million years old, is when we start seeing them walk upright. 2.4 million years ago, we get the genus Homo. And this is where these guys come in. This is Homo erectus. Okay? This is a skull from Homo erectus. Look at what's happening here. Cheekbones, decreasing. Brow structures, decreasing. Still kind of that forward-looking face. But the teeth, much more like humans. This one is a little less defined than this one. And it's just the nature of the scan that I took of the original. I still need to work on brushing this one up. There it is. You can clearly see more of a transition. And even more so, over the 1.6 million years of separation between these, what's happened to the brain? It got bigger. 2.4 million years ago, they start using tools. These rocks have been chipped intentionally for a function. Some were weapons, some were scrapers, some were crushers. They would grind food. They would scrape meat off of skin and bone. They would make weapons, they would make tools. They used these for things. Homo habilis is the first group in Homo to use tools. Okay? They also had humans that are pelvis that are almost directly like proportional and similar to ours. Okay? Now, human pelvis is an interesting thing. When a human mother gives birth, the child has to pass through the pelvic structure, okay, the pelvic girdle. Okay, so that's where the baby is held. The child has to pass through that. The hardest part, for anyone that's not aware of this, is the head. Giving birth to a baby's head. It's the largest, least flexible part of the body. The structure, the hips, the shoulders, any part of the body is still pretty flexible, but the head, you can't get around the size of the head. And human baby heads are very large compared to the size of their bodies. This is a very interesting evolutionary thing, by the way. The biggest holdback for other animals having larger body size is probably head. Giving birth to a head is very difficult, okay? That's why we tend to have litters of one, right? Occasionally twins, very rarely triplets or anything larger than that. Poor Octomom, right? Normally we give birth to one baby at a time, and that is because of the trauma that comes with giving birth to a baby head. Other animals, like dogs or snakes, right? They give birth to tons of groups at the same time because they don't have to worry about that. Brain size small, larger litter size. Brain size big, small litter size. So that's a physical reason, right? Also, there's the nurturing reason. We put way more effort, because we comprehend that it needs to be this way, we put far more effort into raising one young, one offspring. Dogs, they'll raise 5 or 6 at a time, and if one gets picked off, they might grieve for a day and then they move on, right? That's the natural way of things. Snakes couldn't care less. Alligators couldn't care less. They don't notice, and sometimes they even eat their own young, okay? So they have a lot of them because that's what favors them evolutionarily. We have one, maybe 2, and we take great care of them because the investment required for the one offspring is far higher. Okay? So that is both an emotional and a physical reason why it was evolutionarily positive to have larger brains. And having a larger brain led to those other things as well. It's interesting. It's all tied together. Okay? So, back to the point. First tools, 2.4 million years ago. Moving on to Homo erectus, which was this guy right here, 2 million years ago. They also used tools. These are the ones that migrated through Asia and into Southeast Asia out of Africa. Okay? Groups of them wandered across the continents. there are actual, I'm not going to say civilizations, but communities of them that we have in the fossil record out there. We thought they went extinct a long time ago. 800,000 years ago was the most recent one, at least that we thought. But I want to say it was either late 90s, early 2000s, if I remember. They found an ancient community of them that was living on an island as sea levels were rising post a glacial maximum. They got isolated from the rest of the continent on an island in Java. Okay, so out there in the Indonesia area. Okay, and they survived there until about 100,000 years ago. It's pretty cool. The species, Homo erectus, not our species, cousins to us, were alive up until about 100,000 years ago.
There's no way that they're still around.
No. These ones are gone. Let me talk about some other ones, though. Okay. Now, this is kind of a chart that shows you the advantage of, or the difference between having a larger brain size and how fast you mature. Okay. So chimpanzees and Australopithecus and orangutans, their brains, they cap out pretty quickly. They grow fast and their brains cap out quickly. Our brains are born most of the same size that they will be for the rest of our lives. That's the size of a human baby brain. That's the size of an adult human brain. They grow. They almost double, but a chimpanzee brain stays almost exactly the same from birth to death. Okay? All right. Neanderthals. There's this big misconception about Neanderthals. Neanderthal is a word that's often used to describe someone who's being dumb, right? Like, oh, you Neanderthal. Like, you uncultured swine, you Neanderthal. Just, a few of the loving names I hear from my wife all the time. Neanderthals lived in northern Asia and Europe. So as those earlier ancestors move out of Africa and spread through Europe and Asia, the ones that move up north become their own distinct subspecies, which we typically refer to as Neanderthal or Homo neanderthalis. Okay, I think it was Homo neanderthalis is their actual species. Okay, so these guys not only have the same tools as the previous ones, as their ancestors have used for about 1.5 million years at this point. Okay, they not only have those, but they also seem to have some type of culture. I'm talking, these guys are hundreds of thousands of years old, hundreds of thousands of years ago. They had art. They had, they would bury their dead. What is the point of burying your dead if you don't perceive things like love, empathy, I care about you, I am capable of burying your body out of respect, so I am going to. Right? Those are complex brain functions. That's reasoning, that's thought, perhaps even religion. Right? They would bury gifts with their dead as well. Food, flowers, carvings. They would bury them. Now, Neanderthals have kind of a sad story. Neanderthals died out a couple 100,000 years ago. 150 to 200,000 years ago, estimated, right? When another group of Homo primitives, primates, moved into that area and wanted to occupy that same space. Okay, so the Neanderthals went extinct when we showed up. Homo sapiens. You and I, we are Homo sapiens. That is our genus and species. About 150 to 200,000 years ago is the earliest evidence of our species migrating out of Africa and into Europe and Asia. Okay, so we came last. The other groups that went first, they diversified into the groups like Neanderthals and Homo erectus and Homo habilis and all of that. We came last out of Africa. We kind of stayed at home base for a while longer, I guess you could say. But what did we bring with us? We came with the largest brain size yet, with the most evidence of culture and civilization. We came with armor. We came with weapons. We came with a desire to conquer, apparently, because as soon as we showed up, the Neanderthals went away. We see the fossil record, Homo sapiens establishing their colonies in the area, Neanderthals all of a sudden disappear. Is that coincidence? Probably not. Judging by our track record, we probably wiped them out. But we can't have wiped them out entirely because anyone who has ancestry from Northern Europe, you probably have some Neanderthal DNA. My ancestry, I've mapped my genome. Okay, I sent off not mapped my genome, but I've mapped my ancestry. I sent off a copy of my DNA to a lab and they evaluated it. Okay, you can do this, right? They send out kits for you to do this with. I have a little less than 0.001% Neanderthal DNA from my ancestors that come from northern Russia. How is that possible? Unless at least some Neanderthals got incorporated into Homo sapien culture. Now, there are two ways that can happen. Either there was a group of really nice Homo sapiens who were just like, oh, you come join us, right? You be in our community. Or there's the other method of Homo sapiens enslave Neanderthals and do what they want with them. And that's how the DNA ends up in the genome. Okay? Either way, I have both. Both species are represented in my DNA. Okay? And any of you who also have ancestry coming from there, very well, that would be true for you as well. Now, as they come out of Africa and into Europe, they bring with them evidence of the culture that they have developed. What do they have? There is art. The oldest piece of Homo sapien art we have goes back 120,000 years. That's pigment. That's when they were choosing to color things in certain ways. The oldest piece of actual art, like carving and that sort of thing, goes back about 40,000 years. And this is actually a flute that is tens of thousands of years old, found in an ancient Homo sapien community. Okay, this is the wicker and early metal armor that we have found buried with Homo sapiens that were tens of thousands of years old. Okay. Oh, have you guys ever heard of the what do they call that guy? The Midland Man? No? Someone look that up. The Midland Man. This is something I didn't even know about until recently. I haven't added this into my PowerPoint. I only heard about this since the last time I taught the class. Someone find a breakdown on the Midland Man for me. I think it's actually a woman, but they call him the Midland Man.
The ancient human remains.
Yeah.
They think it's the oldest in the world.
Yeah. I think it's the oldest human remains in the New World. How old is it?
10,000.
Yeah. About 10,000 years old. Found here. Yeah, I didn't learn about that until recently myself. Footprints, I know that they are footprints, like out at White Sands, out in New Mexico. They have found fossilized footprints of people. But I didn't know that the Midland Man was a thing until last month. I'll have to do more research into it and incorporate some of that into my lecture. Okay. Climate.
How did the natives get to the Native Americans? But the natives get to
How did they go from Europe and Asia to here? Oh, we're getting there, buddy. We are getting there. We're actually about to start talking on that subject. Okay, so the climate. At the beginning, we start off warm. We're coming out of that Oligocene glacial maximum. Okay, so it starts off pretty warm. Then we get another glacial maximum in the Miocene, and then at the end of the Miocene, we get another warming event. And then we move into the big old glacial maximum again right at the end. Okay, so it goes back and forth. With each change, there's an associated extinction because things have to adapt to be warm and then adapt to be cold and then adapt to be warm again. Back and forth and back and forth and back and forth. Snip, snap, snip, snap, snip, snap. For any Office fans out there. Anyone know what I'm talking about? You guys ever watch The Office? Don't you know what I'm talking about? Okay. When Michael Scott, he gets a vasectomy and then he gets it reversed and then he gets another vasectomy and then he gets it reversed. He's getting frustrated. He's talking to his girlfriend about it. He's like, snip, snap, snip, snap, snip, snap. Don't you know how exhausting that is, right? Or something like that. Oh, come on. All right, so the land bridge between South America and North America forms here. What does this mean? All of a sudden, the things that have evolved here and the things that have evolved here, which have been separated since the Cretaceous, since Pangaea broke up, are now able to swap back and forth. And so we see some species go up here and some species go down here. For the most part, they're pretty distinct, but there are absolutely some crossovers here as a result of this land bridge forming. Then the Ice Age, what we commonly refer to as the Ice Age, was the most recent glacial maximum, okay? That most recent glacial maximum began in the mid-Pliocene and ended at the end of the Pleistocene. So it's not actually the Ice Age. The Ice Age is still going on. Remember that, okay? But this is what the Northern Hemisphere would have looked like during that time. All of this is ice. Ice goes down halfway through Russia, halfway through North America, right? Ice covering all of this. So what brought about this particular glacial maximum or Ice Age? Okay. Well, you guys aren't going to believe this. It's going to totally knock your socks off. It was tectonics. I know. Who could have seen that coming, right? Bwah. So a lot of it actually happened because of the formation of the land bridge between North and South America. That isthmus, that's what we call that. The Panama, that narrow bridge of land, it's called an isthmus. Isthmus. It's very difficult to say, okay? But that land bridge cut off what used to be circulation between the Atlantic and the Pacific. So water would flow between the two continents here, and you would get an exchange of temperature and salts between the two oceans. But now that that land bridge is there, there is no more communication. So the water in the Atlantic flows up north, gets cold, comes down, doesn't get much warmer, and then just keeps circulating around like that, which is why the Atlantic is a colder ocean, and the Pacific is a warmer ocean. The Pacific has more circulation space to warm up its water. The Atlantic is cut off from all that and just keeps recirculating water from the north back and forth and back and forth. So because of that, because the increasingly cold water getting shoved further north, that cooled the temperatures off in the northern hemisphere, which increased the size of the ice cap up there, resulting in this giant glacial maximum that we saw. Okay. Nowadays, we believe our glacial maximum and global warming cycles, those tend to be caused more by Milankovitch cycles than anything. For the last 800,000 years or so, it lines up with these Milankovitch cycles. Yeah. So the obliquity, eccentricity, and precession of Earth around the sun. Okay? So remember our eccentricity, that's our elliptical orbit around the sun. It's not perfectly circular, so at different points we are further from the sun than closer to it, because it's not perfectly circular. Then we have our obliquity and precession, which are the angle of the Earth pointed at the sun and our wobble along that angle. Okay? So we are at this angle, and we're wobbling back and forth on that angle while we go around the sun. Okay? That's Milankovitch cycles. And every now and then it lines up such that we are far from the Earth or far from the sun at the same time that the maximum amount of ice and water is pointed at the sun because of the precession and the obliquity, which means that we reflect more heat than we keep, which means that Earth gets colder, which means that our ice caps get bigger and our snow line drops, and more snow and more ice, which our snow line drops further, and it's this positive feedback loop that goes into a new glacial maximum. Then we come back closer to the sun. We retain more heat, the ice melts, so on and so forth. Okay? It's that cycle. So these, for the last 800, 900,000 years or so, our glacial maximums have generally lined up with the Milankovitch cycles as we go around the sun. Okay? All right. Right. So as far as the landscape goes during this time, it looked way different because of the changing temperatures. Right now, where in a glacial minimum, as we would call it, okay, this is kind of a cross-section of Europe. So like right now, Paris, very nice, beautiful, forested area. Hamburg, Germany, pretty much the same. Moving up north, Stockholm, Sweden, we start moving into more coniferous forests. Even further north of Sweden, which now you're into like Arctic Circle sort of stuff, eventually you break out of the forest and into your tundra and then into your ice cap. But in the same place, during the last glacial maximum, where Paris is right now, would have been tundra. Okay? Very little vegetation, mostly permafrost. Then in Hamburg, Germany, just the polar desert. And where Stockholm, Sweden is right now, would have been under a ton of ice. That was the last glacial maximum, which ended about 12,000 years ago. Okay? We call that the Wisconsin age, the Wisconsin, which it's a period of time even smaller than an epoch, okay? Which I'm not going into in this class, but that's just, if anyone asks you, hey, what was the name of the last ice age? What they really mean is the last glacial maximum, but your answer would be the Wisconsin. Okay. Now, after that ice age ended, it left behind a ton of water. After that glacial maximum ended, it left behind a ton of water. That water went somewhere. Where did it go? It filled in spaces. So we have our Great Lakes underneath. You can see where the ice extent was. Our Great Lakes formed there after all that ice melts. This is Lake Bonneville, which covers most of the entire state of Utah at this point in time. Lake Lahontan, Lake Missoula, and Lake Azazes, okay? Now, of all of these, they are all gone, with the exception of a small piece of Lake Bonneville, which is called the Great Salt Lake. Okay? If you ever look at a picture, a map of North America, of the United States, you'll see the Great Salt Lake hanging out there. That's all that's left of Lake Bonneville. And then we've got, of course, our Great Lakes left over here. The rest is pretty much all gone. The geography. So we get a couple of new mountain building events here. The Basin and Range shows up during this time. The Basin and Range is where, because we are getting the Pacific plate shoved over here and the Farallon plate pushing up here and mountain ranges coming up here, we get a little period, thanks to the physics of the matter, a little section in the middle of North America where we get stretching occurring. So it's being stretched in this little section, which means that we get mountain valley, mountain valley, mountain valley, mountain valley, mountain valley over there between the Rocky Mountains and the West Coast here in the US, okay? It looks almost like sea waves, like ripples on an ocean when you look at it on a topographic map, like a map like we've got over there, okay? That's called the Basin and Range Province. That shows up during this time period. The Sierra Nevadas, which are in California, they show up during this time. That's a whole bunch of mostly Jurassic, ancient Jurassic plutons, so magma chambers, that get shoved up from deep below thanks to the convergence, okay? The subduction of Pacific plate under North America plate, shoving that stuff up tectonically. And then we get the coastal range, okay? So that starts in the Oligocene and ends in the Pliocene. And this was mostly just a whole bunch of volcanic stuff as well. A bunch of volcanoes rose up here. Those volcanoes made their own range. It's the most recent mountain range in North America, the Coastal Range, which you can see it's across the coast of California right here. And then the San Andreas Fault formed here, which is the largest fault in the US. Remember, a fault is just a crack in the ground. It's difficult to tell how long those last in the rock record, because Earth is constantly shifting and moving. Sometimes it's hard to tell how old they really are, how long they last, because of the nature of tectonics. But San Andreas is actually very recently formed. It formed only within the last couple million years. Okay, so pretty easy to tell with that one. And then all of that water in those lakes formed by that melting ice, all of that water has to go somewhere. Okay, so some of it evaporated away, but a lot of it actually ended up evacuating, okay, leaving over a period of time, because all water eventually wants to go down to sea level, right? It's all trying to get to sea level. So when you have this gigantic lake that forms as a result of all that melting ice, eventually it's going to either break through the ice that's holding it in place in front of it, or it's going to make its own river system and push its way down to sea level. Whenever it does that very quickly, it scours the area. We call those scablands. These are scablands out in Oregon from that Ice Age ice that left very quickly after it melted. And then our Himalayas finished rising up during this point in time. So here's India 80 million years ago. It started the collision with Eurasia about 50 million years ago. And then about 10 to 8 million years ago is when India finally finished connecting with that major continent. It's still pushing forward. That convection cylinder is still shoving it forward a little bit, but this is where most of its momentum kind of died out there because it made full contact. And so while it's still pushing, it would be kind of like, it's kind of like a tug of war sort of thing, except instead of pulling, you're pushing. There's not much movement, but the force is still there. Okay. Australia, by the way, is on the same convection cell with it. So you can actually see, when you look at the movements of Australia, you can see in the record of Australia when when India made contact with Eurasia. Because you see, Australia is just kind of like do, and then all of a sudden it goes and starts deviating to the left. And that's because India ran into this continent over here. And then our Alps start rising up during this time as well. Why? What did we just talk about? Africa has run into Eurasia. That's what allowed all of the primates to transfer out of Africa and into the rest of the other continents, right? Well, into Europe and Asia and so on and so forth anyway, okay? Why? Africa ran into it, making that land bridge, allowing the animals to cross that land bridge. But what happened tectonically there? It also created a mountain range. The mountain range, the Alps. The Alps are still climbing. Why? Africa is still moving north. This happened so recently, geologically speaking. Africa is still moving north. Eventually, there won't be a Mediterranean Ocean. It'll just be one big continent of Africa and Eurasia together. Okay? And the Alps are just the beginning of that. Any questions about the Neogene? No? All right, well, we have one more PowerPoint to get through here. The Holocene, the most recent time period. But I'm going to go ahead and pause this for a second. I'm going to go use the restroom, and then we'll pick right back up. All right. I'm back, and it's like I never even left. All right, we are going to cap things off with, oh, why is this still open? Didn't I close that? No. Okay, we're going to cap things off with a conversation about the Holocene, if it will let me. Holocene. Holocene, please. Help! All right, for some reason the recording stopped. I'm going to have to splice these two videos together before I upload it, which is great. I'm glad that I checked, though. All right. All right, the Holocene. This picks up at the end of the Pleistocene. So 11,700 years ago. We are currently living in the Holocene. We call it the Holocene. We have defined it as its own particular time, as its own period, because the glacial maximum ended 11,700 years ago, and modern civilization began at that point. Think about that. Humans, aka us, Homo sapiens, have been around for at least, in our modern iteration, about 200,000 years, right? Since we left Africa, moved into Europe and Asia and all of that. We have gone through multiple sequences of glacial maximum and global warming. Isn't that interesting to think about? Our ancestors survived it without our technology. Just saying. Hope that puts it in a little more positive light for us to be able to pull through this one. They figured it out, so can we. Okay? We have so many advantages. We should be able to manage it just fine. Now, this time period has been characterized by a lot of things, in particular the impact we have had on our environment. We have deforestation, crops, hunting, we've built cities, we have used fossil fuels, that's a big one. Okay, we have had a lot of impact, a lot of influence on our environment. Starting at the end of the Pleistocene, the glaciers retreated. Now, it took a long time for the glaciers to get where they were, and far less time for them to leave. Okay? So this is where the glaciers were 12,000 years ago, right before the end of the Pleistocene. 9,000 years ago, they're here, and then today they are completely gone from this part of the map. Okay? Very, very quick, geologically speaking, for all that ice to go, which is why the Great Lakes are still there, because the crust is still shoved down to the extent that it was when there was ice all over it. And it's still rebounding upward, right? The easiest way, by the way, well, not the easiest way, but one of the common ways to tell things like sea level in recent time periods, when there is no stratigraphy to study for it, right? There's no stratigraphy for the most recent thousands of years, so how do we study sea level rise? Coral reefs. Because coral reefs like to stay in the photic zone, right near the surface of the ocean, where they can get that sunlight, but still get the food that they need in the water. So if sea levels rise, what are coral reefs going to do? They're going to grow up with it, with the seawater, with the sea level, which means that they are going to slowly grow upwards inland to keep up with the land that they need to grow on top of, but still be near the ocean, or still be near the top of the ocean. Sea level fall, what happens? They move further and further down and oceanward. So we can see these trends in coral reefs. And that's how we track sea level rise and fall in recent history. All right. 13,000 years ago, there was a land bridge between Alaska and Russia. And we believe this is when the earliest Homo sapiens walked over that land bridge and entered North America, 13,000 years ago. This earliest civilization is generally referred to as the Clovis people, or one of these early civilizations. One of the largest, more successful ones is called the Clovis people. They seem to have gotten more or less wiped out. Now, I'm not saying extinct. They're the center of their civilization, right? Most of their groups of people seem to have gotten destroyed or scattered by an asteroid impact that happened, an unfortunately located asteroid impact that happened. I said comet here. I don't know why I said comet. I made this a while ago. I just noticed I said comet. I'll have to change that to asteroid because it wouldn't have been a comet. But it landed and killed a bunch of them, and the survivors seem to have kind of scattered across the rest of North America, probably got incorporated into other groups, other cultures and civilizations. Now, eventually, those cultures would organize themselves into the different Native American tribes that we've seen in most recent history, okay? They all came over from Europe and Central Asia, which is why they share most of the same genetic heritage. It's very interesting, though. I've seen a lot of documentaries about the genetics with that are in common with the Native Americans of North America. They have so many genetic markers in common with people from the Middle East and Russia and Asia, and you can see actually which ancestors came from where in the genetics of Native American populations. It's fascinating.
Is it true that horses were once found extinct in Europe and then refound again in North America? Or are those two different species?
No, they're not different species. Horses were brought here by Europeans. Yeah, people came across with them. Yeah, no. I mean, you can go back through ancient history, right? And there are horses, not everywhere, but like in Europe and Asia for sure. I mean, there are cave paintings of horses, right, in France, right, from tens of thousands of years ago. But they were taken to the United States, or not United States, they were taken to North America by these groups of people. reintroduced by Europeans potentially? The most recent record of horses in North America is a very interesting question. I haven't done much research into that. That's a very good question, though. I do know that they have a longer record in Eurasia, though. Okay. All right. Now, about 13,000 years ago, so right as the Pleistocene was ending, right at that glacial maximum was ending, we see a lot of the larger animals. We call them the megafauna, North American megafauna, like our mammoths and our giant sloths and our woolly rhinos, and a lot of them finished going extinct. They were suffering a little before, but they finally finished going extinct. What caused that? What else happened 13,000 years ago? Yeah, people came. Now, is it probable that humans wiped them all out? No. But let's put all the pieces together here. You have a group of predators who are very intelligent and know how to use tools to hunt to make hunting more efficient. They grow very quickly. Their populations grow very quickly. They need to be fed. Yes, they're going to hunt. Humans are going to hunt. But what else is happening in the world at this point in time? It's cold. But what is happening? We're coming out of a glacial maximum, which means what's happening to our temperature? It's increasing. So all these animals like the woolly mammoth and the woolly rhino and the giant ground sloth, they are adapted to cold climates. They need to adapt to warm climates. Things are heating up. All that extra fat and fur, now it's a disadvantage. Now, under normal circumstances, they would have time to adapt. Mutations would occur. Maybe you lose 50, 60, 70, 80% of your population, but the survivors would adapt. They would have mutations that would be positive, that would eventually work their way through the surviving population, and they would recover in a new form, maybe even as a new species. But you introduce a new super predator on the scene, one that is very adaptable, that doesn't leave along with the changing climate. What's going to happen? You lose 80% of your population to climate change, and the rest gets eaten. All of a sudden, you go extinct. It is the intersection of the changing climate plus the introduction of a new species of predator that seems to have wiped out a lot of these giant animals that we used to have here. Okay, so a combination of the climate and human hunting. It's not like all of the humans did a concerted effort to kill every woolly mammoth they could see, right? No, it was both factors together that ultimately led to the downfall of the megafauna. Okay, agriculture, which is the intentional raising of animals and plants as a crop or as a sustainable food source, okay? That started about 9,000 years ago. Earliest evidence, 9,000 years ago, 9,000 BC-ish, so about 14,000 years ago. Okay, so here we have at 8,500 BC, right here, in what is now Greece, what we call Greece, the earliest evidence that people were intentionally growing crops and keeping animals for the purpose of domestication and consistent food sources. Up until this point, people were just kind of wandering around, eating what they could, kind of wandering, finding their food sources, chasing the food. Actually staying in one spot to cultivate your own food, that's agriculture, okay? So 8,500 BC here, 6,000 BC here. In Italy, 5,800. Out here in Spain, 5,400. Out here in the British Islands, 4,000 BC. Now, we see it also happening in North America, right? There is some agriculture done by the ancestral Native Americans. They do a lot of living off of the land, but they also grow their own crops as well, okay? They have their, each different culture developed their own relationship with nature and how they would cultivate it. The oldest living thing we have on Earth today, or the oldest single living thing we have on Earth today, is a tree called Methuselah. It's about 4,500 years old in California, I think is where it's at. This is Methuselah right there. So white pine, white dwarf pine, I believe is what it's called. Okay. How do we tell how old a plant is? Typically, you look at its rings. Okay, the number of rings it has denotes how many seasons of growth it had. Methuselah has a lot of them, being 4,500 years old. Think about the things that Methuselah has lived through. Pretty cool to think about. If only it had eyes, if only it could tell us, right? But the nice thing about trees is not only do the size and the width of the rings tell you a lot about things like the growing season, also you can get isotope readings off of them. And that tells you about temperature variation, precipitation rates, all of the things we talked about before, right? The delta carbon and oxygen ratios, okay? It's also how we track things like the increase of carbon-14 in the atmosphere. We can see that reflected in the plants in their rings through time. Oh. All right, so humans, what have we done? Speaking of delta carbon 14, from 1700 to 2000, look at what happens here. Can you tell where we started burning fossil fuels? Where is the Industrial Revolution? Right there. We see a spike and a drop, and a spike and a drop. What are those drops? We realize there's a fuel. We realize there's something we can use. Here's a convenient coal bed in Great Britain. We grind all that stuff out. We mine the heck out of it, and then it runs out, and we're like, oh, man, now we got to find more. Where are we going to find more? We find more. Boom, 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 boom. Right? We find them in North America. We find coal in North America. Boom, 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 boom. And then, oh, man, we can't keep up, or we've used so much of it. We got to find more. And that's what all these dips and these climbs are, and these dips and climbs. And also, some of these correspond with wars, right? We will see an increase whenever there's a giant war that needs to be fought. Like right here, look at this. In the early 1900s, World War I had an impact. Why? It disrupted production. They needed a lot for the war. A lot of fuel went towards funding the war or fueling the war, and there was relatively few for everything else. But then the war ended. Boom, 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 boom. Look at that. Oh, what do you think that is? What's that right there between 1900 and 2000? That's World War II, right? And then boom, 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 here we are again. Look at this. It becomes a logarithmic scale, the amount of carbon that has been pumped into the atmosphere by fossil fuel use. It's not a straight line. It's not consistently increasing. It is increasing by factors of 10 pretty much at this point, okay? And it just keeps on climbing. We're 25 years past that now, right? It just keeps right on going. It's not sustainable. It's got to stop. But we can't just flick it off. It's got to be something that's done more delicately, something that's done in consideration for continuing our progression of technology and industry, right? It's not just something we can say, oh, just stop, it's bad. That would send us back to, pre-industrial stuff, which would be a disaster. I do not exaggerate. If that happened, if all of a sudden we just flicked off everything that uses fossil fuel, billions of people would die. I am not exaggerating. Billions. Okay? Now, temperature since 1920, which when I made this slideshow was 2020, so it was 100 years, right? Has increased by 1.3 degrees. And is supposed to have increased by about 4 to 9 degrees by 2100. Sea levels are supposed to have risen by about 10 feet at that point, which, if anyone wants to go to Corpus Christi, now's your chance. It'll be underwater, right? Corpus Christi, Galveston, they'll all have water in the streets by the time that happens, okay? This doesn't just affect the atmosphere, though. I mentioned before that there's an intersection between atmosphere and ocean. We call that flux, okay? Ocean-atmosphere flux. They share gases. So whenever there's an excess of carbon dioxide in the atmosphere, that carbon dioxide will translate into the ocean and increase its acidity, which is bad for the things that rely on a certain level of acidity, certain pH levels in the ocean to survive. pH levels get disrupted, a collapse of the food chain. Collapse of the food chain, extinction. And we are actually living through that extinction right now. We are in an extinction. a mass extinction. We are living it right now. Dozens of plants, insects, and animals go extinct every day, which tells you how many our planet had to begin with. But also, again, it's not sustainable. Life will go on with or without us, even if it gets as bad as it'll get. If humanity itself goes extinct because of the choices we've made, which I find extremely unlikely, but if that were to happen, life would still continue without us. It has survived worse than us, but that doesn't mean we shouldn't do our part to try and help the situation. Finding alternatives has to be our option here. I think the best alternatives happen to be nuclear, fission, and fusion. Okay? There are great renewable sources and solar and wind, but those require a lot of resources to construct and keep constructing to keep up with demand. Nuclear, fission, and fusion gives out a lot of energy with much less input necessary constantly. Some cities already, by the way, are getting flooded. Venice, thank you. I was going to say Vienna. It's not Vienna, it's Venice. Okay? This is Venice. It has water in the streets. There are entire buildings, entire sections of that city that are completely underwater. Right? A lot of cities around the world will have water in the streets by the time we hit that 10-foot increase mark. All of these places that are blue, by the way, this is all stuff that is melted. Okay? So everything, all of this ice is gone. So the most recent one on this particular map, this whole red area, that is ice shelf that has been melted as of 2002. Even more of this is true now. I need to get an updated picture for this. But a lot of that ice is gone or is currently melting. That's the Holocene. Interesting times. Any questions about the Holocene? Well then, that is it for our last lecture, guys. You made it. Yay, give yourselves a round of applause. Yay! Thank you everyone for taking my class. We have about 20 minutes left in class. Man, that flew by. Time flies when we're having fun, doesn't it? Okay, that's 20 minutes we can use for final exam review. Please feel free to ask me whatever questions you have. Your final exam is going to be cumulative. It is going to cover all of the lectures. I have made a couple of changes since the last time I offered this class. Let me pull up the final real quick and just make sure that I don't give you wrong information. It's going to open as soon as we're ready, so either in 20 minutes when class closes or whenever you guys decide that you are done with your review. It's going to be due at midnight on Thursday. Okay, so you have 4 full days to take it. You have the normal 500-minute time limit on there. It is 19 questions. Okay. One of the changes that I did, it used to be 20. One of the changes I did that I forgot about until just now was that I combined 2 questions together because they were essentially very similar to each other. But yeah, 19 questions, 500 minutes. That's about 25 plus minutes per question. No reason why that shouldn't be enough time. Okay, no reason for that. Trying to think. What other info do you? What questions do you have about the final? Oh, also you have a lab exam you need to take as well. Both are opening today. Your lab exam, that's going over things like what we learned about the geologic time scale, the organisms that were common during the different points in the time scale, and what the cratonic sequences and orogenies were that we spoke about and when they occurred. Okay? So that'll just kind of be a fill in the blank sort of thing, or as close as I can get to it on Blackboard. But yeah, so you have those 2 exams to take. Questions about any content or format? No questions? All right. Then let me just repeat some of the important things here, okay? Final exam and lab exam need to be turned in. Every lab needs to be turned in. Every discussion board participated in. For my online students, every lecture you need to have participated in some way to get credit. Do not leave anything with a 0 on it. Anything with a 0 can still be turned in, okay? I'm going to be doing a grading pass-through today. I came in early and I went through 1.5 classes of grading. I'll do the other 3.5 here by the end of the afternoon before the first ceremony, graduation ceremony. But I'm going to be keeping up with grading as fast as I possibly can. I know that here at the end, you guys are going to be turning in things fast and thick. But I'm going to keep up with it as best I can. I can't guarantee that for everything you're turning in for the first time, you will have enough time to do a second attempt on. To be honest, you had plenty of time to turn it in already and get it graded so you could have that second or third or even fourth attempt. Okay? But the time is what it is. The only due date I can't change is the one on Thursday. Every single thing is due by midnight on Thursday. Okay? Be here on Wednesday for our movie. That's a little extra credit assignment or opportunity. For those of you online, if you can't be here in person, you can watch the movie yourself and complete the extra credit assignment that way. Jurassic Park. Yeah. Anything else for me? Alma, Joel, are you going to make it on Wednesday? Yeah?
I'm not too sure.
Okay. All right. You going to make it on Wednesday? Huh? You got work? Oh, man. Okay. All right. Well, for those of you that will be here on Wednesday, I'll see you then. But for those of you that may or may not make it, thank you for taking my classes. I've enjoyed having you. Okay? All right. Let's get out of here.